Welcome to this workshop on meta-analysis. In this module, I'll run through a meta-analysis that looks at the impact of exercise on knee pain. The effect size index is the standardized difference in means. This video is one in a series, and I recommend this one if you plan to work with the difference in means or the standardized difference in means. I'll cover the following items: how to enter data, how to run the analysis, how to estimate the mean effect size, how to understand heterogeneity in effects, how to report the results, how to create plots, and how to assess the potential impact of publication bias. I'll be using the software Comprehensive Meta-Analysis, or CMA. Our website is metaanalysis.com. There, you can download a free trial of the software and also the datasets used in this video. Overview. This analysis includes 32 studies that looked at the impact of resistance exercise on knee pain. All studies were randomized controlled trials, RCTs, in which patients were randomized to either resistance exercise or to a control group. Each study employed some scale to assess pain. The effect size index is the standardized difference in means. The results of this analysis will be generalized to comparable studies, and so the random effects model was employed for the analysis. This example is based on data from a systematic review that was published by Jewell, Christensen, Roos, Zhang, and Lund in 2014. If you're interested in the specifics of this analysis, please don't rely on this video, but consult the original paper. Let's start by looking at the data in Excel. The file is called exercise.xls. There's a column here with the study names. There are 3 columns for the treated group. This one has the mean, this one has the standard deviation, and this one has the sample size. And there are 3 columns for the control group. This one has the mean, this one has the standard deviation, and this one has the sample size. I want to copy this data into CMA. I'll highlight all the relevant cells. Notice that I'm including the row with the labels. I click Control-C to copy. I'll open CMA. I'll close this box. I click in this cell, and I click Control-V to paste. Next, I want to take these labels and move them into the header. I click Format, Use First Row as Labels. At this point, the labels are correct, but I still need to identify the function of each column. On the menu, there's a button that I can use to insert columns, and there's a separate button that I can use to identify the function of columns. Since the columns are already in the grid, and I want to identify their functions, I'll use Identify rather than Insert. I click on the first column, and then I click Identify Column for study names. And the program changes the header to study name. I click Identify Column for effect size data. The program opens this wizard. CMA will accept data in many formats, and so I need to tell the program what format I want to use. I also have the option of entering data for some studies in one format, and for other studies in a second format, and so on. At the bottom, I choose Show All 100 Formats, and I click Next. Here, I choose the first option button. This is the one that will allow me to compare two groups. I click Next. On this frame, I choose Continuous Data, Means, because I'll be comparing the mean in two groups. Here, I choose Unmatched Groups Post Data Only. Then, I choose Mean, Standard Deviation, and Sample Size in each group. If I were inserting these columns, the Finish button would light up. Since the columns already exist, and I need to match each column with its function, the Next button lights up. I click Next. I need to identify the column that holds the mean for the treated group. I click here and scroll down to the column labeled Treatment Mean. I need to identify the column that holds the standard deviation for the treated group. I click here and I scroll down to the column labeled Treatment SD. And I need to identify the column that holds the sample size for the treated group. So I click here and scroll down to the column labeled Treated N. Then I need to identify the column that holds the mean for the control group. I click here and scroll down to the column labeled Control Mean. I need to identify the column that holds the standard deviation for the control group. I click here and scroll down to the column labeled Control SD. And finally, I need to identify the column that holds the sample size for the control group. So I click here and scroll down to the column labeled Control N. I also need to identify the column with the effect direction. I'll explain what that is later. However, we don't have a column with that information, so I leave that blank. I click Finish. The program has now relabeled these columns, calling them Group A and Group B. It also opens a wizard so that I can apply my own labels. I'll call this one Exercise and this one Control. I click OK, and the program applies those labels. These columns are now labeled Exercise Mean, Standard Deviation, and Sample Size, and these are now labeled Control, Mean, Standard Deviation, and Sample Size. I need to enter a value for effect direction. I enter Auto for the first study. Then I copy it to all the other studies. Auto means that the program will take the first mean and subtract the second. In general, that's what I want to do. If a high score is good and the treated group does better, the difference will be positive. If a low score is good and the treated group does better, the difference will be negative. The other options here are to set the direction to positive or negative. I would use that if some studies used a scale where a high score is good, for example, how far could the patient walk, while others used the scale where a low score is good, for example, how much time did it take the patient to walk 100 meters. In that case, I would choose positive whenever the treated group did better, and I would choose negative whenever the treated group did worse. In our analysis, a high score is always good, and so we can simply choose Auto. By default, the program is displaying 3 effect size indices. The first 2 are both the standardized difference in means. The first of these is sometimes called Cohen's D, and the second is usually called Hedges' G. The 2 are very close to each other, and we could use either one. However, Hedges' G is slightly more accurate, and so if we have the choice of either one, we'll use Hedges' G. The third effect size index is the raw difference in means. We can only use that if all studies used the same scale to assess outcome. That is not the case here, and so we cannot use that index. To modify this display, I can right-click on the yellow columns. I select Customize the Display. At the top, I choose Set the Primary Index to Hedges G. Then, I remove the check mark for the other two indices. At the bottom, I add a check mark for the standard error and for the variance. And then I click OK. At this point, I'm displaying Hedges G. This would be a good time to save the file. I click the Save icon and I give the file a name. Before I run the analysis, I want to be sure that I know the direction of the effect. In the second study, the mean for the exercise group is higher than the mean for the control group. The effect size is greater than 0, and the treated group did better. So, any effect size to the right of 0 should indicate that the treated group did better. Now I'm ready to run the analysis. I click Run Analysis. At the bottom of this screen, I can choose either the fixed effect model or the random effects model. I choose the random effects model for 3 reasons. First, it allows me to take account of the study-to-study variance when assigning weights to each study. Second, it allows me to assess the dispersion in effect size across studies. And third, this model will allow me to generalize from the studies in the analysis to the universe of comparable studies, which is what I intend to do. Next, I'd like to set the scale for the forest plot. I right-click on the plot, I select Scale, and I set the scale to -4 to +4. I'd like to sort the studies by effect size so that I can get a general sense of how widely the effect size varies across studies. I right-click on the column labeled Hedges G. I click Sort from Low to High. I get the sense that the effect size in most studies falls in the range of around 0 to 1. But there are a few studies with effect sizes larger than that. In any event, this is only intended to give me a general sense of the dispersion. We will compute the actual dispersion momentarily. This column displays the effect size, which is the standardized mean difference. This column displays the standard error. This column displays the error variance. This column displays the lower limit of the mean. This column displays the upper limit of the mean. If I wanted to test the null hypothesis that the effect size is 0, I would use these 2 columns. This column gives me the z-value for that test, and this column gives me the p-value for that test. And finally, I want to display the sample size for each study. I click this button, and the program inserts a column with the sample size. First, let's look at the mean, or the pooled estimate, of the effect size. The pooled estimate of the effect size is 0.629. We see that here and here. On average, in the universe of populations that are comparable to those in the analysis, exercise will increase the outcome by roughly 0.63 standard deviations as compared with a control. The confidence interval tells me how precisely we've estimated the mean. The confidence interval is 0.46 to 0.80. We see that here and here. The mean effect size in the universe of comparable populations probably falls in the range of 0.46 to 0.80. If we wanted to test the null hypothesis that the mean is 0, the z-value for that test is 7.235 with a corresponding p-value of less than 0.001. We see that here. And we also see it here in that the confidence interval excludes 0. Next, I'd like to know about the dispersion in effects. Typically, at this point, we would report the Q value, I squared, and tau squared. I'm not going to do that. Instead, I'm going to take a few minutes and talk about what we actually have in mind when we ask about heterogeneity. Then, I'm going to show that these statistics do not actually tell us what we want to know. And finally, I'm going to introduce a statistic that does tell us how much the effect size varies across studies. To avoid confusion, let me address a common mistake. A moment ago, I spoke about this line, which reflects the confidence interval. Many researchers believe that this line tells us something about the dispersion in effects. It does not. It tells us how precisely we've estimated the mean effect size. It says nothing about how widely the effect size varies from study to study. This line is sometimes displayed as it is here, and is sometimes displayed as a diamond, as it is in this version of the plot. But in either case, the meaning is the same. The confidence interval is an index of precision, not an index of dispersion. It tells us nothing about how widely the effect size varies across studies. To get a general sense of the heterogeneity, I can sort the studies by effect size as I did a moment ago. However, this plot is not as informative as we might expect for several reasons. In particular, the distribution shown here is the distribution of observed effects, which includes sampling error. What we really care about is the distribution of true effects, and that is what we would see if we could somehow remove the sampling error. To compute the actual amount of dispersion, we do something similar to what we would do in a primary study. We compute the standard deviation of the true effects, and then we compute an interval based on the mean plus or minus 2 standard deviations. If we can assume that the effects are normally distributed in the relevant units, we would expect that the true effect size in 95% of all comparable populations will fall within that interval. I'm going to switch to a plot that actually shows the entire distribution of effects. Unlike the current plot, which shows the effects only for the populations in the analysis, this shows the distribution of effects for the universe of all comparable studies. I've set the scale to go from minus 2.5 to plus 2.5. An effect size of 0 would indicate that the treatment had no effect. Any effect size to the left of 0 would indicate that the treatment was harmful, and any effect size to the right of 0 would indicate that the treatment was helpful. An effect size of plus 1 would indicate that the treatment improved the outcome by 1 standard deviation. An effect size of plus 2 would indicate that the treatment improved the outcome by 2 standard deviations, and so on. The mean is 0.63. I'll plot that here. I can add the confidence interval and the caption. The caption reads, the mean effect size is 0.63 with a 95% confidence interval of 0.46 to 0.80. In other words, we estimated the mean as 0.63, but the true mean could fall anywhere from here to here. As I mentioned before, all of this deals with the average effect size. It says nothing about how the effect size in individual studies varies from the mean. Let's look at that now. In a real analysis, I would simply plot the distribution of true effects. However, for the purposes of this video, I'm going to present 3 possible distributions and then ask which one applies in our analysis. I'm doing this to make it clear what we have in mind when we ask about heterogeneity. Here is one possible distribution. This line shows the distribution of effects. At one extreme, there are some populations where the effect size is 0.14, and at the other extreme, there are some populations where the effect size is 1.12. The actual numbers are presented in this caption, which reads, "The true effect size in 95% of all comparable populations falls in the interval 0.14 to 1.12. This interval, 0.14 to 1.12, is called the prediction interval. If I was asked to predict the impact of treatment in any one population, selected at random from the universe of populations comparable to those in the analysis, I would predict that the impact would fall in this interval, and I'd be correct some 95% of the time. In the other 5% of cases, the true effect size would fall to the left of here or to the right of here. So the prediction interval simply gives me the endpoints of the plot. Or does the distribution of effects look like this? At one extreme, there are some populations where the effect size is minus 0.18. At the other extreme, there are some populations where the effect size is plus 1.44. In this case, the prediction interval is minus 0.18 to plus 1.44. Or does the distribution of effects look like this? At one extreme, there are some populations where the effect size is minus 0.76. At the other extreme, there are some populations where the effect size is plus 2.02. These are 3 possible examples of what the distribution of effects might look like. Of course, there are an infinite number of other possible distributions. I've picked these 3 to illustrate my point, which is simply that when we ask about heterogeneity, this is what we have in mind. We want to know what the distribution of effects looks like. Why is it important to know which of these applies? Well, if the distribution looks like this, we would conclude that the size of the effect varies substantially. There are some populations where the impact of treatment is small, but there are also some where the treatment improves function by a full standard deviation. Critically, all of the effects fall to the right of 0, which tells us that there are no populations where the treatment is harmful. By contrast, suppose the distribution of effects looks like this. Here, there are some populations where the treatment improves outcome by as much as 1.5 standard deviations. At the same time, there are some populations where the treatment is harmful, but these effects occur in only a small proportion of cases, and in these, the harm is not large enough to be clinically important. And finally, suppose the distribution of effects looks like this. Here, there are some populations where the treatment improves outcome by as much as 2 standard deviations. From a clinical point of view, this would be exceptionally useful. At the same time, the treatment is harmful in a substantial number of populations, and in some cases, the harm is clinically important. So, which of these 3 plots corresponds to the actual distribution of effects in this analysis? Because this is so important, I would assume that this information is included in any paper that reports the results of a meta-analysis. As it turns out, however, I would be wrong. There are 3 statistics that researchers typically report to describe heterogeneity. To see these statistics in CMA, I click Next Table, and I scroll to the right. The statistics are presented here. These are the Q value along with its degrees of freedom and a p-value, the I-squared statistic, and tau squared. However, as we will see momentarily, these statistics don't actually tell us how much the effect size varies. The first statistic reported is the Q value, along with its degrees of freedom and the p-value. In this case, the Q value is 103.110, the degrees of freedom is 31, and the p-value is less than 0.001. On that basis, does the distribution of effects look like this, or like this? The answer is there's no way to know. It could be any of these, or something else entirely. The next statistic reported is I-squared. In this case, I-squared is 70%. On that basis, does the distribution of effects look like this, or like this? The answer is there is no way to know. It could be any of these. I recognize that this statement will probably come as a surprise, but ask yourself this. I've given you the value of I-squared, which is 70%. Which of these plots actually corresponds to the distribution of true effects? You may or may not guess correctly, but your choice will be a guess because I-squared does not provide that information. And finally, the last statistic typically reported is tau squared, the variance of true effects. In this case, tau squared is 0.151. On that basis, does the distribution of effects look like this, or like this? It actually is possible to determine which of these is correct based on tau squared, but few people know how. So, what statistic does tell us how much the effect size varies? That statistic is called the prediction interval. Here I would report that the true effect size in 95% of all comparable populations falls in the interval minus 0.18 to plus 1.44. And that corresponds to this distribution. Where do I locate the prediction interval? If I'm using CMA version 4, I can simply click this button and the program creates this plot. If this looks different from the plot that I showed before, that's only because this plot is using a different scale. The caption reflects the information in the distribution. It reads, the true effect size in 95% of all comparable populations falls in the interval minus 0.18 to 1.44. If you're using an earlier version of CMA, or if you're using another program entirely, you can still create this plot. To do so, you can download a free program on our website. You would simply enter 4 values as shown here. The mean effect size, the upper limit of the confidence interval, tau squared, and the number of studies. And then click Next to create the plot. At this point, I've explained that the key statistic to address the dispersion in effects is the prediction interval. What about the other statistics? What do the p-value, I-squared, and tau squared tell us? Later in this video, when I explain how to report the results of a meta-analysis, I provide a one-sentence description of each. However, to actually explain what each of these tells us is really a separate lecture. For those of you who are interested, the lecture is available at metaanalysisworkshops.com. And this is also addressed in the text Common Mistakes in Meta-Analysis and How to Avoid Them. The relevant chapter is available for free as a PDF on the book's website. I encourage you to take advantage of these resources. A primary benefit of a meta-analysis is that it enables us to see how the effect size varies across studies. We should always be sure to report this information and to do so in a way that is clear and informative. That is, by reporting the prediction interval. There is one very important caveat to all of this. In order to estimate heterogeneity reliably, we need a minimum number of studies in the analysis. The number of studies needed will vary based on several factors. However, we might use 10 as a useful minimum. When there is variation in effects, and there are less than 10 studies in the analysis, we cannot have confidence that any of the statistics related to heterogeneity will be reliable. This includes I-squared, tau-squared, and the prediction interval. Now let's have a look at how we might explain the results. In CMA version 4, I click this button and the program displays this page, which reads as follows. Overview. The analysis is based on 32 studies. The effect size index is the standardized difference in means, G. The results of this analysis will be generalized to comparable studies. Therefore, the random effects model was employed for the analysis. And here I would indicate what an effect size on either side of 0 represents. For example, that it favors the treated group or the control group. What is the mean effect size? The mean effect size is 0.629 with a 95% confidence interval of 0.458 to 0.799. The mean effect size in the universe of comparable studies could fall anywhere in this interval. The z-value tests the null hypothesis that the mean effect size is 0. The z-value is 7.235 with a corresponding p-value of less than 0.001. Using a criterion alpha of 0.05, we reject the null hypothesis and conclude that in the universe of populations comparable to those in the analysis, the mean effect size is not precisely 0. How much does the effect size vary across studies? The Q statistic provides a test of the null hypothesis that all studies in the analysis share a common effect size. If all studies shared the same true effect size, the expected value of Q would be equal to the degrees of freedom, which is the number of studies minus 1. The Q value is 103.110 with 31 degrees of freedom and a p-value of less than 0.001. Using a criterion alpha of 0.10, we can reject the null hypothesis that the true effect size is the same in all these studies. The I-squared statistic is 70%, which tells us that some 70% of the variance in observed effects reflects variance in true effects rather than sampling error. Tau-squared, the variance of true effect sizes, is 0.151 in G units, and tau, the standard deviation of true effect sizes, is 0.389 in G units. If we assume that the true effect sizes are normally distributed in G units, we can estimate that the prediction interval is minus 0.185 to 1.442. The true effect size in 95% of all comparable populations falls in this interval. Please note that my intention here is not to have the program write the report. I'm simply trying to ensure that statistics are interpreted properly. Next, we might want to create a high-resolution version of the forest plot. I click High Resolution Plot. I click Reset All. I want to set the dimensions of the plot to match the newer version of PowerPoint. If I'm using version 4 of CMA, that will be the default. If I'm using version 3 of CMA, I would click File, Page Size, and Margins. Then I would set the width to 1600 and the height to 900. I'll leave the left and right margins at 50, and I'll change the top and bottom margins to 20. I right-click on the title. I edit the title to Impact of Resistance Exercise on Pain. I click Font and click the button with one red arrow twice to reduce the font size. I right-click on the plot and click Spacing and Forest Plot Width. There's an area over here called the right buffer. This leaves space on the right side of the forest plot in case I want to add additional columns there. In this case, I don't, and so I want to remove the buffer. I click Right Buffer and Remove. I want to add space between the columns. I click Column Spacing, and then I click the button with one blue arrow 2 times. I want to increase the size of the plot. I click Forest Plot Width, and I click the button with 2 blue arrows. The 2 sides of the plot are labeled Favors A and Favors B. I know that the left should be Favors Control and the right should be Favors Exercise. I know that because I checked this on the data entry screen. Now I can enter those labels here. I right-click on Favors A. I enter the labels Favors Control and Favors Exercise. I click Font, and I click the button with one blue arrow 2 times. I'd like to send this to PowerPoint. I click File, Export to PowerPoint. The program opens PowerPoint and inserts the plot. Back in CMA, I can also choose colors for slides and modify any or all of the colors. For example, I could set the colors to look like this, and then send this to PowerPoint again. I can also send it directly to Word. Or I can save this image as a file and then import it into any program. Next, let's generate a high-resolution version of the distribution of true effects. I simply click this button to get the plot. I can edit almost any element on the plot. I'll change the title to Impact of Resistance Exercise on Pain. Again, I can click File, Export to PowerPoint. That's it for the basic analysis. When we analyze a primary study, we typically perform a sensitivity analysis. This means that we might perform a series of analyses to ensure that the results are robust. For example, we might want to ensure that the results were not overly influenced by one outlier. We can do something similar in a meta-analysis. Here, I'll outline 3 procedures that we might want to include as part of a sensitivity analysis. One issue that we might want to explore is how much of an impact each study has on the analysis. Recall that the summary effect size is a weighted mean of the individual effect sizes. we might want to see how much weight was assigned to each study. If I click this button, I can display a column with the relative weight assigned to each study. Initially, these bars are on a scale of 0 to 100. To see the weights more clearly, I can right-click here, and then I choose Scale Relative to Maximum. This changes the scale so that the differences among weights are easier to see. Additionally, I can sort by relative weight. I right-click on the weights, and I select Sort from High to Low. It looks like no study gets more than 5% of the weight, and that is reassuring. If there were 1 or 2 studies that dominated the analysis, we would want to call attention to that in the discussion and also identify the impact of those studies on the basic conclusions. For example, we would want to know how much the effect size would shift if those studies were removed from the analysis. In this case, there is no study that dominates the analysis, and we can say that in the report. I'm going to resort by effect size, and to hide the weights, I'm going to deselect this button. Also, as a kind of sensitivity analysis, I might want to assure myself that no single study is responsible for the essential conclusions. In other words, suppose that there was one study which happened to have an extremely low effect size. If this study were removed from the analysis, the mean effect size might shift substantially, and the heterogeneity in effects could become substantially smaller. This does not mean that we would want to remove that study from the analysis, but we would want to be aware of its impact on the analysis and discuss that as part of the report. In this analysis, it's not likely that any study will pose this kind of a problem, since no study receives more than about 5% of the weight. However, let's run through this as an exercise. At the bottom of the screen, I have a tab for basic stats and a tab for one study removed. I'll click on the tab for one study removed. Now, the row labeled Chang does not show the results for Chang. Rather, the row for Chang shows the results for an analysis based on all studies except for Chang. On the row labeled Chang, the effect size is 0.651 with a confidence interval of 0.4802 to 0.822. And this is what I would see on the yellow line if we ran an analysis using the other 31 studies. As I scan the set of analyses, I see that regardless of which study I remove, the basic conclusions remain unchanged. The mean effect size never moves to the left nor to the right by enough to change the clinical implications of the finding. And if we're concerned about a test of the null hypothesis, the p-value is always less than 0.001. So, this plot allows me to report that the results are robust in the sense that the conclusions remain essentially the same with any one study removed. I'll click Basic Stats to return to the standard analysis screen. Next, I'd like to perform an analysis for publication bias. The logic of publication bias is discussed at length in another module. Here, I'll focus on the results. To look at publication bias, I click this button. I go to Computational Options and I click Random Effects. The program displays what is traditionally known as a funnel plot. The large studies are plotted at the top and the small studies are plotted at the bottom. Most models of publication bias assume that most of the large studies have been published. That's because large studies tend to be statistically significant even when the effect size is relatively small, and even when these studies are not statistically significant, there are various incentives to publish them. Therefore, we expect large studies to be evenly distributed on either side of the mean. By contrast, we expect that only some of the smaller studies have been published. Specifically, small studies that reported large effects would tend to be statistically significant and likely to be published. We see those here. By contrast, small studies that reported smaller effects might not be statistically significant and might not have been published. So our concern is that there might have been small studies that were performed and showed effects in this area, but those studies were not published and therefore are missing from our analysis. One method for addressing this is called the trim and fill method. This approach tries to estimate how many studies might be missing over here. It then creates those studies and adds them to the analysis. At the moment, we're looking at the studies that were actually included in the analysis. If I click this button, I can see the actual studies plus the imputed studies. The trim and fill method estimates that there may be 6 studies missing. It created those studies and added them here. At the bottom, we see the mean effect size based on the actual studies and also what happens when we add the missing studies. The original mean was here, but if these studies were missing and we add them to the analysis, the correct mean would be here. To see the actual numbers, I click View, Trim, and Fill. I'm using the numbers for the random effects analysis. The original mean was 0.63, and the adjusted mean is 0.44. Let's go back to the plot. The original mean was 0.63, and the adjusted mean is 0.44. There have been a number of developments in thinking about publication bias. One of these is that researchers now realize that if small studies tend to have larger effects, as they did here, there are several possible reasons for this. One possible reason is publication bias. In other words, it's possible that these studies were performed but not published. Another possible reason is that the effect size really is larger in the smaller studies, and what we're looking at here could be the full set of studies that were performed. The reason that we see studies here but not here is that small studies actually do tend to have larger effects. For example, smaller studies might have been conducted by people who were more meticulous in performing the intervention, or smaller studies might have enrolled patients who were sicker and therefore tended to show more improvement. For this reason, when it turns out that the effect size is larger in the smaller studies, we now refer to this as a small study effect rather than publication bias. In other words, if the effect size really is larger in the smaller studies, our best estimate of the mean effect in the universe of comparable populations would be 0.63. On the other hand, if the effect size in the small studies looks like this, and these studies are missing, the correct effect size would be 0.44. So we don't necessarily know which one of these is likely to be correct. What we can do is to think about the clinical implications of one effect size or the other. In this analysis, one could argue that even if there was publication bias, the essential conclusions would remain the same. In other words, the clinical utility of the adjusted effect size is similar to that of the original effect size. I need to point out 2 technical issues with trim and fill. First, we need to tell the program whether small studies are expected to be missing to the left of the mean or to the right of the mean. We always expect that small studies are more likely to be missing if they are not statistically significant. And that means that they would fall closer to the nil value. In this analysis, the mean effect size falls to the right of 0, and therefore we expect studies to be missing to the left of the mean. I click View, Trim, and Fill. I click Look for Missing Studies on the left side of the mean. This happens to be the default. If I had wanted to look for missing studies on the right of the mean, I would need to make that selection here before looking at the plot. Second, there's an option here to look for missing studies using either the fixed effect model or the random effects model. By convention, we use the fixed effect model to look for missing studies, even though we'll be using the random effects model to compute the mean effect size. The program also performs various other tests for publication bias. Using the View menu, I can also display the failsafe N, the rank correlation test, and the Egger test. I can also click View, Show Report, Show All. If I do that, the program creates a report that discusses the results for all the publication bias tests. For example, it says about trim and fill, under the random effects model, the point estimate and 95% confidence interval for the combined studies is 0.629 with a confidence interval of 0.458 to 0.799. Using trim and fill, the imputed point estimate is 0.442 with a confidence interval of 0.242 to 0.641. For a complete discussion of meta-analysis, consider subscribing to our workshops. These are now available online as well as in person. For information, visit metaanalysisworkshops.com. This is also where you can download the free program to compute prediction intervals. In this analysis, I used the software Comprehensive Meta-Analysis. For information about the software, please visit metaanalysis.com. My name is Michael Borenstein. My email is michael@metaanalysis.com. Please feel free to contact me with any comments or questions.